Imagine you're writing a book. You start with a draft and want to turn it into a market-ready book. You hire a team of an editor, marketing specialist, and a designer. Editor fixes grammar, marketing adds an appeal for potential readers, and designer creates a cover. Together, their collective effort turns the draft into a market-ready product. In order to ensure that the essence of the draft is not lost, it's added to the output of the teamwork. This example illustrates how residual learning works. Here, draft is an input to the stack of layers and it's defined as x. Market-ready book is a desired output, h of x. And f of x is an incremental improvement that team made to x, meaning that instead of directly learning h of x, the network learns residual function f of x, which is basically h of x minus x, that simplifies learning process and allows to train very deep networks. The idea comes from 2015 paper called Deep Residual Learning for Image Recognition. And the residual learning concept is explained in section 3, where authors say that rather than expect stack layers to approximate h of x, we explicitly let these layers approximate a residual function f of x, which is h of x minus x. The original function thus becomes f of x plus x, as illustrated by this building block figure, where x is an input to stack layers and y is an output, and it's an element-wise addition of residual function f and input x. And residual function here is configured by two layers defined by w1 and w2, and ReLU activation function is applied after first layer, and second nonlinearity also ReLU is applied after addition. f of x is usually implemented using multiple layers, with 2 and 3 being most popular choices. And when we add more layers, it allows model to represent more complex transformations. However, with just one single layer, it's just a linear transformation of x. So authors also claim that they haven't seen any benefits of this configuration. Main problem that authors are addressing using residual learning is when the network gets deeper, the performance degrades significantly. And they also share an example of training two networks. One is 20 layer and another one is much deeper, 56 layer deep network. They train it on a CFAR10 challenge. As you can see, the deeper network has higher training error and thus test error. Authors also claim that this problem is not caused by overfitting. It's also not caused by vanishing gradients problem, because they applied batch normalization to all networks, which is one of the most popular solutions to this problem. Let's talk about residual learning in transformers. Transformer is a residual network. There is a great paper called A Mathematical Framework for Transformer Circuits, written by team in Anthropic in 2021, that provides great insights into how transformers work, with one of them being about residual learning. So they focus on decoder-only model, and I took this picture from tutorial written by JLMR that clearly explains the architecture. And transformer decoder model predicts next token in a sequence given previous tokens, and consists of a stack of decoder blocks. Each one of them is a pair of mask self-attention and feed-forward neural network / MLP. And mask self-attention consists of multiple heads running in parallel. So coming back to this paper, they also have a very good explanation about the architecture of this model, that starts with embedding layer of the token, followed by what they call a residual block, and followed by unembedding. So a residual block in this definition is a pair of attention layer and MLP layer. And the paper says that each attention layer and MLP layer reads from a residual stream, they call it a residual stream, by doing a linear projection, and then they add linear projection back to this residual stream. So you can see here that, for example, xi is an input to this attention layer that after doing some calculations adds the linear projection back to the residual stream, and it becomes xi plus 1, which is then an input to MLP. So residual stream is just simply a sum of all the outputs of the previous layers plus the token embedding. And they say that residual stream, it's better to think of it as a communication channel because it doesn't do any processing by itself, but all the layers communicate through it. Both attention and MLP layers read and write to residual stream by doing linear projection. The residual stream dimension is batch times sequence length times embedding dimension. Attention layer then reads it through multiplication by weight matrices WK, WQ, and WV. The result is key, query, and value matrices that are then passed to calculate attention for each of the head. Stack of attention matrices are then concatenated and then multiplied by WO that produces attention output matrix of the same dimension as of residual stream. This is the right operation. MLP layer consists of two linear transformations. It reads from the residual stream by applying a weight matrix W1 to the input. After applying nonlinearity like JELU, it then performs another matrix multiplication by W2 to get the output of shape, batch times sequence length times embedding dimension that's written back to the residual stream. Another interesting insight shared in this paper is that residual stream has a high dimensionality and therefore can be divided into different subspaces. And each subspace is dedicated for different kind of information, can be dedicated. For example, this residual stream shown on the picture is divided into 3 subspaces, and for example, first subspace might contain information about like a previous token, or second subspace can store something like the subject of the sentence, etc., etc. And if layers read and write to the same subspace, then they communicate to each other. However, if they do it to different disjoint subspaces, then they don't interact at all. Another claim that this paper made was that bases of residual space are not anyhow special, therefore the basis is non-privileged. And then this paper, published in 2023 in Anthropic, called Privileged Bases in the Transformer Residual Stream, showed that in practice it's a wrong claim. Authors first introduce us to a context and talk about another paper called 8-bit matrix multiplication for transformers at scale, written in 2022. Researchers in this paper examined hidden layers of a transformer and found outliers, specific neurons that produce unusually high activation values compared to others, up to 20x larger. They first appear in 25% of all transformer layer in small models, and then affect all layers when model reaches size of 6.7 billions. These outliers are highly systematic at the 6.7 billion scale. 150,000 outliers occur per sequence, but they are concentrated in only 6 feature dimensions across the entire transformer. To understand the importance of these features, researchers created an experiment where they first created an alternative version of the model where they set outliers to 0 in a hidden state that goes to the attention layer. They also say we do this for all layers independently, meaning we forward the regular softmax probabilities values to avoid cascading errors and isolate the effects due to the outlier features. They also created another control version of the model where they set neurons to 0, but this time randomly. They compare the performance of these three models using top 1 softmax probability and validation perplexity. And results are interesting. So they see that in a model where they set outliers to 0, they reduced softmax probability from 40% to 20% and increased validation perplexity by 600 to 1000%. Like, this is huge. And in a model with random where they set neurons randomly to 0, they reduced softmax probability by only between 0.02 to 0.3% and increased validation perplexity by 0.1%. So these results completely indicate the importance, like the critical importance of these outliers to the model performance. And a natural question that arises from interpretability viewpoint is, what are these features, what do they represent, or what purpose do they serve? And why are these features basis aligned? If you are not sure what I'm talking about when I say that features are basis aligned, check out my other video when I talk about fundamental concepts for mechanistic interpretability, including privileged bases. To answer these research questions, team in Anthropic conducted experiments using their own 200 million parameter model. And first, they suggested to use a metric to detect outliers in activation vector. And the reasoning was following. So if we think of activation vectors as random direction, then the property of this is that every element of this activation vector is drawn from isotropic Gaussian, followed by normalization to a unit vector. So if we have, for separate token, if we have activation vector as following a1, a2, a3, etc., then we can think that each of these elements is drawn from Gaussian. Then, if we scale the activation vector to unit norm, then we can calculate the kurtosis, which is a measure of tailiness, right? So if a kurtosis is 3, this means like it's a normal distribution with no heavy tails. Otherwise, if it's much larger than 3, it signals that there are some extreme values. And we can repeat these calculations for several tokens and take the average. And team in Anthropic shared with us the plot they created where they measured the kurtosis for each of the layer in their own 200 million parameter model. And you can see that the values are very large, signaling the outliers. To test that metric works correctly, they also did the rotation of the bases to see if vector values will be distributed more equally across basis directions. So to illustrate this, imagine, so this is the basis in which transformer works. So it's like 2D with basis corresponding to some meaningful features like gender and royalty, with a man as an activation vector. So you can see that it has very high value for gender and 0 value for royalty. So it's basis aligned. But if we rotate the basis, change it, you can see that the values are equally distributed along basis directions. And if we plot, after doing the rotation to transformer activations, we calculate the kurtosis again and plot its values. So you can see that the values are again 3. So this signals that activation vectors are Gaussian distributed. To understand what causes these large values in activations, team ran few experiments and they had 3 hypotheses. And the first hypothesis is to suspect that LayerNorm has something to do with it because it has a mean subtraction and per channel learned weight that both might introduce basis dependency. So just to make it more illustrative, we have value activation vector x, then we subtract a mean from it, and then we calculate it by these learned parameters gamma and beta. And they might potentially introduce basis dependency. I took this picture from Arena tutorial. And then researchers, what they did as an experiment, they introduced modified LayerNorm, where they changed the subtraction of the mean and just did the scaling. And they also used a single learnable scale parameter. And they claimed that after this, model should be rotation invariant. When they calculated the kurtosis using this updated LayerNorm, what they saw are again these large outliers. That led to conclusion that LayerNorm is not causing any outliers. Hypothesis 2 was to think that maybe limited numerical precision causes model to favor certain directions, because this way model can prevent large values from overshadowing smaller ones. So what I mean by this is that let's see just a simple large and small numbers summation in Python represented using NumPy flow32 type. And one number is 10 to the point of 8. A small number is 10 to the 10 to the power of -2. When we add them both, we expect to see this value at the bottom. However, the result is this, so we lose the second digit. And the setup of this experiment was to rotate every parameter matrix between read and write operations from residual stream on a forward pass. And then they checked the performance of model using change in loss. And the result was that change in loss was absolutely tiny, suggesting the model is generally rotation invariant even when accounting for floating point error. So again, just to make it more illustrative, let's go back to this example. So if the model is basis aligned, so we should see large values here, right? And if we rotate the basis, then the values of this vector should be equally distributed across basis directions. Finally, the last hypothesis they tested was that maybe there is something in a combination of limited numerical precision and gradients. And the experiment was very similar to the hypothesis 2 test, but this time they rotated not parameter matrix but activations, again between read and write to residual stream, and during training and not forward pass as before. And they again checked the performance of a model using change in loss. They had two setups for this experiment. So if this is a residual stream and we have two layers, MLP and attention and many more, then in the first setup, these layers, they share rotation matrix. So it's the same for each of the layer, for every layer in the transformer model. In the second setup, though, every layer has its own rotation matrix. So every layer operates in its own basis. And the result of this experiment was that they didn't see any difference between baseline model, between shared rotation and independent rotation, so setup 1 and setup 2, on a training loss. And the conclusion was that transformers do not rely on a privileged basis to train and function properly, even when floating point precision is taken into account. And when they also looked at the activation after the model reads from residual stream and rotates to a new basis, and before it passes it to MLP to process, they looked at the kurtosis of this activation, and they again saw very large values. And the conclusion here was that basis alignment is an artifact of the computation inside of the transformer layers, more so than from the representation in the residual stream.